Today we are going to discuss about cross-section design resistant to shear. This design resistance is covered in clause 6.2.6 of Eurocode 3 part 11. The design requirement is the VED, that's the design value to shear, over the VCRD should less than or equal to 1.0. The VCRD is the plastic design resistant to shear, is the area of shear times Fy over square root 3 over gamma m 0. And the area, the AV is area of shear. It is can be calculated based on clause 6.2.6 in bracket number 3, Eurocode 3 part 11. And for the UB and UC, so the area of shear is basically the this area. So from this diagram, so it can be very clear that the shear resistance is controlled by the shear, by the web. So the big role here is the thickness of the web and overall depth. The beam of the cross section. So it is quite direct. It's only to determine the area of shear, and then by default there is a reduction in strength of the material, Fy over square root 3, and value of the gamma m0 is equal to 1.0. You can find this in clause 6.2 6.1 note 2b Eurocode 3 11. And then a beam, when it is simply supported subject to uniform distributed load, directly it determine, we can determine directly the design resistance, the shear diagram, shear force diagram. So at the middle of the span is equal to 0 when the minimum maximum when the bending moment is maximum, the shear force is minimum. Okay, so then we repeat. Cross-section design resistance to shear is covered in clause 6.2.6 Eurocode 3 part 1.1, and then the design requirement is VED is the design value to shear over VCRD design resistance, cross-section design resistance to shear should less than equal to 1.0. Then the VCRD is equal to V plastic RD equal to area of shear times strength of material over square root 3 divided by gamma M0. So the area of shear can be determined. So basically, it is calculated is measuring from the area of the web, and then you can find the expression in clause 6.2.6 in bracket 3. So when we discuss about when we do verification on shear VCRD, there are two possible conditions that need to be considered as well. Number one, if the HW over TW bigger than 72 epsilon over nu, where the nu is 1.0, so then we have to go further to verify the web from Shear buckling. So only if the HW over TW bigger than this expression. So the slenderness ratio overall, the slenderness ratio of the web under the suffix of the flanks. So the web shear buckling verification is in section 5 of Eurocode 3 part 1.5. Section 5. Number 2, if the VED, the design value of shear, is bigger than 0.5 V plastic RD, bigger than 0.5 V plastic RD, so we have to replace the cross-section design resistant to bending moment into the reduced value. So it means if VED bigger than 0.5 V plastic RD, basically it is there is high shear area. So high shear area. So what should do here? So do here is reduce the nominal tensile strength. tensile strength to this value 1 minus rho Fy. So then the rho is 2 VED over V plastic RD minus 1 plus bracket square. So then we have to use this expression in order to determine the cross-section design resistance to bending moment. Or else you can calculate the reduce bending cross-section design resistance to shear this MYVRD by using this expression. Is the modulus plastic buat Y minus rho AW squared over 4 AW times Fy over gamma M 0. And then but the value, the MYVRD should less than equal to MYCRD. So all this explanation is stated in clause 6.2.8 of Eurocode 3 part 1.1. So it has happened when there is high shear area. So we have what we need to do when there is high shear area. So we have to reduce the dominant tensile strength. So then, so it means we replace the MYCRD cross-section design resistance to bending moment about Y axis to by using this expression. The Fy just tensile strength, nominal tensile strength using this expression, or else we calculate using this MYVRD. The value of AW is HW times TW directly. And then this MYCRD is calculated MYCRD Fy times modulus plastic buat Y over gamma M 0. Then we can find this one in clause 6.2.5 Eurocode 3 1.1. So when it is happen, this one, for the this one, basically like this. On a simply supported beam, when it is subject to uniform distributed load plus point load P. So basically the design, the shear force will be like this. And then the bending moment will be slightly shifted like this. So there is high shear area here. High shear area. So it is not necessary to calculate the high shear area or reduce the design resistance to bending moment MYCRD by MYVRD. It is only need to be take care if the VED bigger than 0.5 V plastic RD. So the key important thing here is this one. And then the possible arrangement of load case is like this diagram. There is point load in between the span of the beam. So then there is a high shear area. Okay, there is the shear design resistance. So we will continue our discussion to the example